In this video, we will be discussing how to derive the equation that describes the position of a particle that is launched as a projectile. Here we can see the particle initially it's at the origin, it's launched at a velocity v. We have two axes, x and z, and these are the two equations that describe the motion of the particle at any given time t. So we'll be discussing how to get these two equations. And alpha is the launch angle. So let's start from the beginning. So the equation of motion for a projectile under gravity is the following. Here I'm denoting a vector with a line and the derivative with a dot. This is the time derivative. So in this case, this is the same as writing the following. This is just the second derivative of r. So this really is the acceleration of the particle, and this is gravity. This is the acceleration due to gravity. And of course m is the mass of the particle. In this case, we will assume that it is a vector of constant magnitude. So g doesn't change over time. In general, this is an assumption you can make when solving these sorts of problems. If we choose the z-axis to be the vertical direction, we get the following equations for the accelerations in the various different directions. So let's say that we have a coordinate system, a right-handed one, say it's x, y, and z, and in this case, if we have just gravity acting on the particle, we have the acceleration in the x direction be equal to 0. The acceleration in the y direction is also equal to 0. And the acceleration in the z direction is actually equals minus g, which is 9.81. But these are the equations that describe the acceleration. So in this scenario, since the particle will not be moving in the y direction, we don't actually need coordinate at all. So we'll be left with just x and z. Thus the motion is effectively two-dimensional. Now we're left with just x double dot equals 0 and z double dot equals minus g. So let's start with x double dot. This really can be rewritten as this equation. This is equal to 0. And so what we do now is integrate both sides of this. So we take the integral. With respect to dt. And so when we take the integral, now we'll have just the first derivative of x with respect to time, but we also have a constant to take into account. This is due to the integration. And what do we do now? We integrate again, of course, in order to get rid of the derivative. And so now the integral of a constant, this is an easy integral to solve, and what we get is x equals another constant, we can call this integration constant a, plus b times t. And this t comes from integrating this constant here. So now we have the first equation that describes the motion of the particle. Currently it's not in the form that we saw earlier, so this one, but we'll talk about this later. First we need to show where these equations come from. Next we need to do the following for z. So we start from z double dot equals minus g. Again we integrate both sides. Integral right, like this. Yep. And the result is, of course, here we're left with first derivative. We have an integration constant, and since we're integrating g, we also have minus g t to the first power, from this integral. And this is t, if it's not obvious. Now we need to integrate again, of course. And what happens is on the inside we have two integrals. Minus integral gt dt. So now, after we integrate both sides, we get another integration constant, and at the end we get z equals c plus dt. This is not the same dt as here. This is here d is an integration constant and t is time, minus half g t to the second power. And we have this equation now. Now we have the equations for x and z, where a, b, c, d are constants that can be fixed by the initial conditions. For this case, the initial conditions will define the initial x and z position of the particle. In this case, there will be a and c, and the initial velocity, b and d. So if I was to, so what I'm talking about is, if I was to write these again, in this equation, what a and c are, these are the initial x position of the particle and the initial z position of the particle, and b is the initial x velocity of the particle, and d is the initial z velocity of the particle. These will be set by the initial conditions of the system. So, for example, let's say that we have a projectile and we want to determine what the possible range of a projectile is. The projectile is launched from the surface of Earth, and let's assume that the Earth is flat. Obviously the Earth is flat. And let's say that the projectile is launched with a velocity v at an angle to the horizontal, and we want to determine what is the range of this projectile, how far can it go, and we want to have an equation that describes this. We may choose the point of launch to be the origin, and initially the time is set to 0. So let's draw our picture. Let's not just talk. This is X, this is Z, this is our origin. So A and C will effectively be 0. Projectile is launched. There's some angle with respect to the flat plane. And we want to determine how far it can go. So we want to determine x max, some sort of value. So since the launch is from the origin of the coordinate system, x0, which is A, and z0, which is C, will be 0. As a result, we'll have the following case. So now we need to determine what B and D are. And these will really be the initial velocity in the X and in the Z. And so how do we do this? Of course we can use this angle. Let's draw a little picture of just the angle. So this is x dot, and this is z dot. And what happens here is the sine of alpha equals z dot v, and v is just the initial velocity of the particle, and also the cosine of alpha equals to x dot over v. And of course, as a result, we can write that z dot equals v sine alpha, x dot equals v cos alpha. And these equations, as we have mentioned multiple times, this one is actually equal to D, and this is equal to B over here. And so now we can rewrite these two equations the following way. And we also have z here So now we have the two equations that we actually saw at the beginning. We have derived them. And we can, of course, continue. We can do stuff with these equations. So we want to determine what is the range, how far can this projectile be launched. As a reminder, the angle will be 45 degrees in order to achieve x max, the maximum distance along the x, but we'll see why. I'll show you why that is. So, what happens when the projectile hits the ground? Well, z becomes 0 again. Initially it is 0 and it will again become 0. As a result, we take this equation and we set z to 0. 0 equals vt sin alpha minus a half gt squared. And of course we can rewrite it in a better way. We can rewrite it as half gt squared equals vt sin alpha. I'm skipping a couple of steps here because I'm putting this on the other side and I'm cancelling the minuses. You should be able to see where I'm coming from with this. And so now we can see that we have at on both sides. The second power is cancelled by t on the other side. And we also want, we can't hit, let's also solve for t. And what in this case t will represent is the time at which the projectile hits the ground. Because as we set z to 0. So t ground, this will equal to 2v sin alpha over g. And this is the time when the projectile will hit the ground after it has been launched at an angle alpha. And velocity v, and g is the acceleration due to gravity. So, of course we set out to determine what x max is. And we'll get there. Reminder, we previously wrote that x equals vt cosine alpha. And we also have this equation. And we can substitute the t ground over here. X equals v times 2v sin alpha g cos alpha. And we're basically there already, actually. X max, actually x, just x for now, x equals 2v squared cosine alpha sine alpha g. And this is the equation that actually describes the x position of the particle when it hits the ground. and it's launched at alpha angle above the horizon with a velocity v. And so how do we determine the maximum range? Well, this can be done by you can plug in various different angles, and if you were to do so, you will see that when alpha equals to 45 degrees, which is also pi over 4 radians, x is maximized. We get the maximum value of x. So if we want to have the x max value, the maximum range, we write 2v squared cosine pi over 4 or 45 degrees. Either of the two is fine. Pi over 4 over g. This will be equal to 2 over 2. This will be 2 over 2 as well. I'll just write it explicitly so that everything is clear. 2 v squared over 2 over 2 g. These will cancel. And the result will be the maximum value of x equals to v squared divided by g. And so if we want to launch, so this is the equation that you can use to determine the range of a projectile, and it's maximized when we set the angle at 45 degrees. So I hope this video has been helpful, and if you have any questions, I'm more than happy to answer them. Thank you.